Assalamu alaikum everyone. My name is Adnan Hassan and today I along with Osama Zahid and Hafsanur will be presenting our project which is the implementation of static synchronous compensator for the improvement of voltage stability. We will start with a brief background of our device. We aimed to create this device to tackle a problem that has long plagued this nation's power sector: poor voltage regulation on transmission lines. I'm sure all of us here has witnessed flickering lights and varying fan speeds at least a couple of times in our lives. We believe that by deploying devices like a Statcom, we will be able to greatly improve our voltage regulation. But what exactly is a STATCOM? A STATCOM is a power electronics device that controls the reactive power flow through a power network and thereby increases the stability of the network by either absorbing or generating reactive power in synchronization with the demand. Our device is connected between the grid and the load and is located at the transmission line. We measure the line voltages and current at the point of common coupling through our current and potential transformer. This goes into our STATCOM controller that manipulates the values and checks if there is any deviation from our rated conditions. If so, it generates reference signals that is sent to the voltage source converter. The voltage source converter basically takes those impulses and generates a voltage difference which drives a reactive current to or from the grid, thereby regulating the line voltages and improving the power factor of the system. In this slide, we can see our simulation overview. Starting on our left, to model our grid, we have an 11 kV generator acting as our bulk power source. Connected to that is a 60-kilometer transmission line, split into two 30-kilometer segments that is further connected to our base load of 22 MVA. The STATCOM is connected in the middle of our transmission line because that is where we found it to be the most effective. Our main transformer is connected to the load and is rated at 22.45 MVA with 11 kilovolts on the primary side and 433 volts on the secondary to induce transient effects that create voltage fluctuation. We use 10 MVA inductive load switched in for zero point 0.1 seconds from 0.45 to 0.55 seconds of our simulation, which induces an undervoltage condition. And for overvoltage, we connect a 10 MVA capacitive load switched in for 1 second. Our switchgear and protective circuit follow the EC2271 standard, which are set for medium voltage lines. Although much of the information about this standard had to be paid for, we were able to learn that it follows the normal inverse time characteristics of the IDMT relay, with time multiplier settings set at zero point 0.4. The panel previously asked that by injecting large amount of reactive currents into the grid, do we not run a risk of tripping the protective system? So I will try answering this by using the IDMT curve shown. During peak STATCOM power injection, if we assume that 2 times the rated current is flowing, then our current PSM would be 2, and at relay time settings of zero point 0.4, it will take more than 2.5 seconds of consistent current injection for the relay to trip and the line to shut off. I'd like to emphasize that our device is only meant to deal with transient faults that last less than a second. Under sustained voltage drops or spikes, the protective system will act. Our device won't in any way help avoid that. Looking at the STATCOM response, from this diagram we can clearly see the advantages of using a STATCOM. Both graphs show line voltages of the same grid, with and without a STATCOM. The graph on the right shows severe voltage fluctuations due to transient faults, while the one on the left with our STATCOM connected shows stable voltage throughout. Now we'll be looking closely at the performance of STATCOM at under voltage conditions. The red line shows the grid without the STATCOM, and we can clearly see that under transient faults, the voltage drops to about 0.92 per unit, which is an 8% decrease of the rated voltage. With our STATCOM attached, voltage is stabilized at 0.97 per unit during the same fault, which shows a 5% voltage regulation. Now, moving on to the overvoltage performance, we see a similar trend. As we can see, the line voltages surge to 1.4 per unit without a STATCOM attached, but with a STATCOM, we are able to bring down the voltages to the rated 1 pu. So now we look at the reactive power compensation that is provided by our STATCOM. There were two transient conditions that we introduced into the lines to check the performance of our device. The first was a transient fault that induced an overvoltage condition from 0.45 seconds to 0.55 seconds. We can see from the graph during this time our STATCOM absorbs reactive power, therefore stabilizing the line voltages. During this second transient, we face an overvoltage condition from 0.75 seconds to 0.85. Our device rectified this by delivering reactive power back into the grid. With these graphs, we can prove that our STATCOM simulation does exactly what we designed it to do. It regulates voltages through reactive power compensation. The maximum compensation it can provide is 6.7 MVA, roughly 0.3 pu of the rated power of the system.
In the last presentation, we were asked about why our system was not on an 11 kV or 132 kV grid since STATCOM is a transmission and distribution compensation device. The reason we could not choose these ratings is the testing limitations. There were two possible means of testing, real-time site testing and bare hardware in the loop. We would like to specify that it would have been impossible to get access to 11 or 132 kV grid lines since they are highly dangerous and only experienced personnel can handle them. As an alternative, we plan to test our system with a very interesting method called hardware in the loop, which will be discussed in the succeeding slides. But we were disappointed to find that the HIL system, even though very important for power electronic testing, were unavailable in any educational institute throughout Pakistan. This forced us to choose a 220-volt system for our testing rather than what was initially planned. Moreover, we would like to promptly highlight that the project is primarily designed to provide proof of the concept that static systems can compensate active or reactive power. Also, the panel had repeatedly asked us the benefits of application on 220-volt system. We want to bring it into view that the controller we promised to design is compatible with any voltage rating. There are no specific benefits to using it on 220 volt, but it is not important what rating we choose, it is important that we get the pulsed output right. Hence, whether an 11 kV or 220 volt system, the controller will provide with corresponding pulse signals to trigger inverter to produce the reactive power. Following this information, we designed a 220-volt grid upon which we simulated our controller to achieve the desired outputs. Coming on to the HIL mechanism as promised. Testing of control systems has traditionally been carried out directly on physical equipment in the field or on full systems in the lab. While offering testing fidelity, this practice can be very expensive, inefficient, and potentially unsafe. HIL is a possible alternative, which is a type of simulation, real-time simulation. You can use HIL simulation to test your controller design. It shows how your controller responds to real-time realistic virtual stimuli. You can also use HIL to determine if your physical system, that is the plant model, is valid. HIL testing offers an excellent alternative to traditional testing methods. When performing HIL simulation, the physical plant is replaced by precisely equivalent computer model running in real time on a simulator appropriately equipped with inputs and outputs capable of interfacing with control systems and other equipment. In this way, the HIL simulator can accurately reproduce the plant and its dynamics together with sensors and actuators, providing comprehensive closed loop testing without the need for testing on real systems. There are two types of hardware in the loop equipments we came across, that is Opal RT and DSpace. Unfortunately, we did not have the means to use any of these devices. Although cost effective, the equipment is very expensive to buy individually. We would like to emphasize that if such equipment is made available in the future, students like us can test power electronic controllers with great ease and accuracy for various industries. Now that we had established that the system will be 220 volt, we designed a grid in the lab and observed voltage irregularities upon addition of reactive load. This was done before the university closed due to the unfortunate spread of COVID-19 pandemic. Since we are currently unable to access labs, we decided to simulate the system at home. The results observed in these simulations were also visible in the lab. As in the lab, we connected three-phase voltage source via transmission line to rated domestic load. In the simulation, the resistors in between are mimicking the transmission line resistances. In parallel to these loads via breakers, heavy reactive load was connected. When these loads were switched in, spikes were observed. A similar system is simulated here. Let us observe the voltages in normal conditions at 220 volts. As you can see, they are all at rated 220 volts. Now running the simulation, waiting for the transients to resolve, and then switching in the heavy reactive load to observe spikes. As you can see, the voltage has dipped. Removing it back to observe it return to its original position and switching it back in. The aim of the Statcom is to control these spikes in real-time systems.
From here, I'm going to guide you about the implementation of our Statcom controller that can also be called as the brain of our project. As you can see, the Simulink diagram of our project controller, whose input are three-phase voltage and current and whose output are six signals, which are a switching signal goes to the inverter, which produces the corresponding reactive power based on these switching signals. This is the inside of my Statcom controller. I'm going to burn this controller on some hardware which is a microcontroller. In order to do that, I have to divide this whole system into subsystems, which I have to program individually. And after that, I just have to combine them to make the whole system, which can be recorded as a Statcom controller. So the first system we have to program is PLL, and the second is ABC to DQ converter. The third and the fourth are these voltage regulator, but as you go inside of them, it's only general PI controller. So I can program a single PI controller and use for both of these subsystems, but with a different value of a constant. The next and the last thing is the inner current control loop. Now let's see inside of it and then divide it further with the different subsystems. Now inside of this inner current control loop block, you can see the two voltage regulator block. This can be programmed same as the previous voltage regulator block with a different value of Kp and Ki. So we have only left with the two blocks, which are DQ to ABC and the last one is SPWM. So these are 5 whole subsystems. The next step is to program each of them individually and combine them to make the whole controller.
We have selected Arduino Uno to program my subsystem because we have already worked on it and it's easy to code. From all the subsystem, ABC to DQ is seem easy to be implemented. So we first implement this block on Arduino. But this block needs omega T4 transformation, which is the output of other subsystem called PLL. So at the first we consider omega T to be equal to 50 Hz. So this is my window of Arduino IDE where we code ABC to DQ subsystem, and this is my simulation window. You can see that a three-phase input is going to the port A and the output is going to the port B. Each input and output are monitored by oscilloscope. In this slide you can see the output of oscilloscope. On the left side it's my input, which is three-phase signal, and on the right side it's output, which basically a DQ0 signal. We have checked this output by comparing it with the Simulink result, according to which we have successfully implemented ABC to DQ block on Arduino. So while working on Arduino, we have faced a lot of obstacles, but among all of them, implementation of PLL was the major obstacle because of the following reason. First, Arduino processor doesn't have floating point unit. A floating point unit, also known as a math coprocessor, is a specialized coprocessor that manipulates numbers more quickly than the basic microprocessor. The requirement of FPU is not only limited to PLL, but a lot of my project blocks required FPU to be processed. The second reason is that Arduino is a single core CPU and it's unable to do a parallel instruction execution. Basically, my algorithm requires a different instruction to be executed parallel, so it's impossible to do with Arduino. The third reason is that there are no any resources for implementation of these blocks on Arduino available. This means we have to start from scratch. The fourth most important reason is that Arduino doesn't have that much processing power to execute this algorithm. We will discuss this point further in next slide. So these are the 4 points that we have chosen as a selection criteria for the selection of microcontroller. Most of you will agree that this thing should be done before carrying out work on Arduino, but we realized this mistake later. So from these 4 points, first 3 points are cleared in selection of microcontroller, but for the last one, we have to find the required processing power. One processing a real-time signal, it's just like we take an input from analog to digital converter, which is same as a train of samples in such a way that the processing should be done in a single sample before the arrival of the second sample. So from this we concluded that the processing power is dependent on the following factor. The processing power is depending upon the time budget, the time between the samples, and the time budget are further dependent on the sampling frequency. From this formula you can say that higher is the sampling frequency, more lower is the time budget. The second factor is the number of operation cycles per sample required by algorithm to completely process. In my case, it's equal to 10 million operation per sample. This means 10 million operations should be performed on a single sample for my code to completely process. We can calculate the required processing power for a sampling frequency of ADC corresponding to some microcontroller and then compare it with the processing power of the same microcontroller. The first is the calculation of a processing power when my microcontroller is Arduino. So the Arduino have a clock frequency of 16 megahertz. The speed of Arduino will be 16 million instructions per second, and we have chosen the maximum prescaler of ADC. This is because we have to find the minimum sampling frequency which will be corresponding to the maximum time budget. So from that way we can find the maximum processing power of Arduino. So the minimum clock frequency of Arduino is, but in Arduino each conversion take a 13 cycle. So the minimum clock frequency of Arduino become 9615 Hertz. This means that in 1 second 9615 samples are there. Then the time budget will be 10 millisecond. From the time budget we can calculate that how much processing power a microcontroller need to process my algorithm, which is equal to 1000 million operations per second. But if we compare this to the speed of Arduino, then we deduce that Arduino can never process the algorithm. Arduino doesn't have that processing capability to process this algorithm. So now we have to find which microcontroller to choose. We have studied the architecture of a lot of microcontrollers to match our selection criteria. And we have found, after studying thesis papers and consulting with a different processor, that in academic and industry, the DSP is being used to implement power electronic project. We have found that the DSP is available in our university, which is DSP TMS 320C613, whose clock frequency is 225 MHz, and the maximum instruction this DSP can execute in one clock cycle is 8. So the speed of DSP is 18,000 million instructions per second. On the right side, you can see us working on DSP, but before we have worked on that, we had calculated that either this DSP have that much processing capability to run our algorithm or not. So the same calculation is carried out for the DSP that I have carried out for Arduino. From this, you can see that we have a time budget of 12 milliseconds, and if we divide the number of operations required by our algorithm to this time budget, we will get the required processing power, which is 833 million operations per second. So from this, we conclude that the DSP have that much processing power which our algorithm required. While working on the DSP, we were exploring new areas of our knowledge, but along with that, we have encountered a lot of problems, and these problems made it impossible to implement our project on DSP. First problem was we have analog simulation of our project, which we have to convert it into a digital simulation by using bilinear transformation. In order to perform this step, we have to know the transfer function of our system, including all subsystems. But we had made the whole simulation without any specific mathematical model, as it mostly based on head and trial method. But we have found a tool in MATLAB which can find the transfer function of built-in Simulink model. We had tried that once too, but after a multiple tries we were get a gains instead of transfer function. Then we figured out that our subsystem are not LTI system. These are non-LTI systems, so that's why the transfer function doesn't exist. At this point we were confused. We had no idea how to proceed next step in our project, but our teachers taught us to never give up. So we start aggressively researching another way, and we have encountered with one of a master thesis of a student from Politecnico di Tirano, Italy, who uses a STM32 microcontroller to build the same project, but he used a tool which is provided by MATLAB called embedded target tool, which can easily convert the whole Simulink diagram directly to the code and burn it on a microcontroller. So we grab this opportunity and we start working on it. So we have found STM32F40VGA, which is based on a high performance ARM Cortex M4 32-bit processor and operating at a frequency of 168 MHz. On further research, we have found that its processing power is 1.25 dry-strong million instructions per second per megahertz. Basically, this is the unit of finding the processing power as compared to the VEX 11780 machine, which means this processor is 1.25 faster than VEX per megahertz. While reading its data sheet, we conclude that it also implements full set of DSP instructions, but by the proof of the master thesis of Politecnico di Tirano, we are 100% confident that this microprocessor have that much processing power which our algorithm require. Along with these things, this microcontroller have the corresponding embedded target tool provided by MATLAB. This means we don't have to program this microcontroller. We only have to use embedded target tool to convert our Simulink diagram and burn it on the microcontroller. While we were doing this, we have no idea of the future, and suddenly the whole world hit on a pandemic because of a COVID-19, and we were quarantined in our houses. At this situation, we tried to work on our project, but our project required oscilloscope and function generator to further proceed. So at this point, we have no any way to further work on our project, but we never gave up. I started searching for an oscilloscope in the market, but I found it so costly, about $400 for oscilloscope and $300 for function generator. So I have searched in a Pakistan market and I found an unassembled oscilloscope kit. So I have no any choices to buy this and assemble this oscilloscope and make it work. It seems very difficult, but I got the unassembled kit along with some manual paper including the instruction. So I tried it and I succeeded. These are the picture of the assembled oscilloscope. Next step is to make a function generator. I found an assistant software that can be act as a function generator and produce a required signal through a sound card. For this I need a cable and then connect the cable and then observe the output signal. And I was succeed. I got the accurate signal output that was shown by the software. But the problem is that it only produces a single phase signal. And in my project I required a three-phase signal, mean a three-phase source. So after a research I come to the point that Arduino can be used to produce a three-phase signal by using a sine pulse width modulation. So I code the Arduino, and you can see at the left this moving picture basically shows the output of sine pulse width modulation at port 9, 10 and 11. On the right side, this is the simulation diagram of my Arduino, and the potential divider is connected in such a way by varying it you can vary the magnitude of output waves from the Arduino. On the next we will move towards the demo. Thank you so much.
This mathematical model is of blinking LED, which is the blue LED present on STM32. This mathematical model I have built to test that either MATLAB can successfully first convert the mathematical model in a code form, and can code form be loaded on this microcontroller. This microcontroller is attached with my PC. Now, before burning it, I have to initialize the ports of microcontroller, which can I easily initialize is through this window. This is the target form. These are the all ports, and I have initialized the port D pin 15 from this window. Now let's burn the code on microcontroller. So from this you can see that the LED start blinking. So this means that the code has successfully loaded on the microcontroller. This window will automatically pop up after the burning the code. This window is the result of the code which have burned. It consists of these files. Basically, our mathematical model is converted into this code file and then loaded on the microcontroller. From the previous demo, we have burned a blinking mathematical model which was in Simulink to our STM3204 by using an embedded toolbox. Now in this demo, we are going to burn our Statcom controller. This is our Statcom controller to STM3204. This Statcom controller is basically connected with a 3 input of ADC, which is basically a 3-phase voltage, and this one is a 3-phase electrical current. These inputs are going into the controller. Basically, these inputs are taken from the grid, and this controller will do the processing on these 6 signals. On the basis of that, it produces a 6 output, and this 6 output is basically a pulsating output which given to a switch of the inverter to produce the required reactive power, which then injected to the grid. Now let us burn this mathematical model to STM3204. For this, first I connect this with my PC, and after connecting this with my PC, you can see that its lights turn on, and I have to push this button and wait for about 2 minutes. You can see that it's still processing. Mainly this MATLAB uses an embedded toolbox to first convert this mathematical model into a code form, and then it will start loading on our STM3204. So we have to wait for a while. Now you can see this LED is blinking. Now this LED start blinking, mean the load is processing on a microcontroller. The code is processing on a microcontroller. Oh, now we get the report. This is the report of the complete accomplishment of the task, which basically show a different code files. These are the code files. All of these code files are corresponding to these mathematical model converted to these code files, and then it loaded on the STM32 successfully. Whole setup is basically a function generator. This is an Arduino which is connected with this circuit. It's a LC circuit. These are the 3 phase which is coming out from the Arduino. We're gonna examine the single phase that is sinusoidal or not in this oscilloscope. This first wave is connected, and now this phase is basically connected with an LC circuit, and this LC circuit is connected with the oscilloscope. And this is the second and the third phase. Now if you go back to the oscilloscope, you can see that it's a 490 Hz and a sinusoidal wave. Now if we disconnected the first phase and connected the second phase, now this second phase is connected with the same LC circuit, and this is going into the oscilloscope. You can see a sinusoidal with a phase shift of 120 degree and have the same frequency and the same magnitude if you see this oscilloscope. Now if we disconnected this phase, and this is the third phase. Now we are going to examine the third phase, either it is sinusoid or not. If we connect this, you can see the same sinusoid with the 250 240 phase shift and the same frequency and magnitude. So this whole setup is basically a function generator to generate a three-phase signal. The demo of our project. Basically, this is the function generator. This function generator will give us 6 signal. The 1 3 is the 3-phase voltage, the other 3 are a 3-phase current. These three these 6 signals, these are the 3-phase voltage, these are the 3-phase current, will goes to this breadboard. There are an LC circuit. Each signal is corresponding to the each LC circuit, and LC circuit is act as a filter. Now at the output of the filter, and wires connect these signals to our ADC of microcontroller. As we know that there are 6 signals which are coming from the ADC and going to the controller, and controller is outputting a 6 pulses to the 6 switches of the inverter. So these are our signal which is going into the ADC. This is our microcontroller will undergo the processing in these signals, and the output will come from this pin, which we can monitor from this oscilloscope. Now here, if we want to change the magnitude of the signal, we can change it by this potential divider. This potential divider, which is connected with an Arduino, and is capable of changing the magnitude of the output signal. Now let us examine the output or the working of our demo. Now the Arduino has connected to the PC. The Arduino is sending the signal to the LC filters, which is the 3-phase voltage and the 3-phase current. Now this microcontroller will be generating a pulse. I have connected this one of the pin into the output of my pulses. Now you can see in this oscilloscope the pulses is generating. This pulses is basically 10.014 Hertz, and these pulses will given to a switches of an inverter, where it can switch it on and off to produce the corresponding electric power. Now if I disconnected the PD3 and connected to the PD2, which is another the one of the output of my switching signal, then you can see this switching signals pattern. Now this pattern is according to how much reactive power should be injected into the grid, and now I can also change it to the PD4, which is again another output of my. Now you can see the switching signals. This is the switching signal is good, should go to the inverter, where the inverter will change the reactive power output from the capacitor injected to the grid. Now I will change this potential meter, changes the which changes the magnitude of the input signal to the microcontroller. Now now you can see the width of this signal changes according to the magnitude of the input. If I change it more, if I change this potentiometer to more, you can see that its frequency changes 3 Hertz, 3 Hertz frequency from 2 Hertz frequency. This is, and now it's 4.3 Hertz. Changes this potentiometer, which changes the input to the microcontroller, which then changes the switching signal.
Now, moving on to the final part of our presentation. This is the project budget. The system cost us rupees 14,885. Following this, we have the Gantt chart of our activities. Finally, the network diagram is panned out in front of you. Lastly, we would like to thank our supervisor, lab teachers and assistants, and our panel members in assisting us throughout the project and leading it towards its completion. Thank you.